Hi, so this lecture is to look into a 2-degree of freedom systems of having a input of or what we call force vibration using a method what we call modal analysis. The learning objectives are as follows. We want to make sure you understand the principle of modal analysis, transform the physical coordinates of a system into principal coordinates. So make sure you know the term physical coordinates and principal coordinates. And we want to determine the force response of an undamped 2-degree of freedom system using what we call modal analysis method. So let us take a look what it means by modal analysis concepts. So as you see here, we have this figure, which is quite common to 2-degree of freedom system with mass, springs and dampers. So if you remember, we already derived these equations in our previous lecture 10, and we can see here that in this system you do have a couple matrix, a couple stiffness matrix. So this is in the form of what we call the generalized coordinates using x1 and x2. So we assume in this case that it is without damping, so that's why you don't see any damping matrix. So if you see in this matrix, so basically you can also see that for each of the equations there is an expressions of x1 and x2 there. So this is what we call the coupling, where we call it as a static coupling, where your stiffness matrix is non-diagonal. Okay, so in this case it is static or elastic coupling. If you have a mass stiffness that is non-diagonal, then you will also have dynamic coupling, which we have seen this in a previous lecture. Okay, so it may occur, okay, but in this case you can see that the mass is uncoupled, because you can see these two are zeros, means for each of the for the first equation you only have x double dot 1, and for the second equation you only have x double dot 2 for m only. So in this case is only the stiffness is coupled, or you have static coupling. If you could imagine, if the system of equations could be uncoupled, so this is a very important fact, if it's uncoupled, so we can obtain diagonal mass. Okay, what it means by uncoupled means both mass and stiffness matrices basically are diagonal. Then each of the equation would be similar to that of a single degree of freedom system. Yeah, it's like a 2 single degree of freedom system. So these equations can then be solved independent of each other. So this is a very important point. So the process of deriving the equations of motion into independent set of equations is what we call modal analysis. Or I would rephrase that as I shown here. Basically, you want to change from decoupled equation of motions to uncoupled equation of motions. So this process is what we call modal analysis. We'll see that in a minute. The coordinate transformation that is required is one that decouples. So how do we actually decouple it? Basically, we use another coordinate that you can transform it, okay, in terms of inertially and elastically. So we want to have both the stiffness and the mass matrix to be uncoupled, so that it will give you a diagonal matrix of mass and also a diagonal stiffness matrix. So this is what we want to have. So we want both to be diagonal at the same time. So it has been proven that if the mass of stiffness is post and pre-multiplied by mode shape and its transpose respectively, the result is some scalar constant. Okay, so we introduce one of the matrix, okay, in terms of mode shape vectors, okay, and we denote it as this phi. Okay, we already have at our disposal previously, so this we're gonna use as the necessary coordinate transformation. How we do that, we'll show you. The new name of a variable that we want to transform is from x to eta. So basically we are using our mode shapes matrix phi, okay, or what we call the modal matrix, okay, phi, and eta vector is called the principal coordinates. There are a few names to it: principal coordinates, normal coordinates, or modal coordinates. Okay, those are the same names. It's just saying why we want to do this is we want to first transform x, which is the generalized coordinates that we have now, maybe x1, x2, x and theta, into another set of coordinates eta, which is eta1, eta2, eta3 and so on, okay, by using your mode shapes vectors. So let us take a look how we go about doing that. So let's say we have written the EOM in terms of the matrix. So now we have in equation 4, basically we put it in a matrix form. So take note that we are still using x double dot and x, yeah. So this x double dot will be x double dot 1, x double dot 2, and vector x will be x1 and x2. And with the corresponding mass matrix and stiffness matrix. So after that, if we substitute, so this is the original EOM. Then if we substitute equation 2 into equation 4, if you remember, basically equation 2 is this equation, okay? So you have x, if I write that down here, equals to your phi, okay, matrix phi. So take note of the notation. All the squiggling bracket is basically your vector, whereas square bracket is your matrix, yeah. So here you have these 2 into 4, so you get this equation. Okay, you can see here all the expressions. So everything in terms of this is actually your x double dot, and this is actually your x. Okay, maybe I do like that. This is basically your x. So we have substitute directly, and then you pre-multiply by the transpose of the modal matrix, and we obtain as such. So you can see that we pre-multiply. So here, okay, we pre-multiply everything. Okay, if you remember in linear algebra or your matrix operation, anything that you pre-multiply with transpose and then you post-multiply with another with the original matrix, you can actually get diagonal. So if you remember, if you have something like this, then you can get diagonal matrix. Okay, the diagonal elements of mass is what we call MD, and the diagonal element for K is KD. Okay, so these are the diagonal matrices. So if you write that down, so therefore you can see that equation 6 can be written as equation 9 now. So basically from this, maybe I just show that again. So this equation 6, basically this whole thing is actually diagonal for new matrix for mass, which is diagonal, and this whole thing now becomes your K. Okay, this is according to the identity or properties of how you get diagonal matrix by pre-multiply it with transpose and post-multiply it with the original matrix. So that's why you get equation 9. So now everything you can see, these two are already in diagonal form. So from there, when it is diagonal, that means for each of the equations will be independent. Okay, so maybe in the next video you can see one of the examples, so you can easily understand how we solve for this. Then from there, you can actually represent it in terms of n, and you can solve for your forces using the single degree of freedom system solution. So in other words, maybe if you want to depict or illustrate the process of what we're doing here, is you can see in this illustration where it actually, or if you look at this figure, so this is the original system. So basically after you transform, you break it up into two single degree of freedom systems. So two single degree of freedom system as shown on the right hand side of this figure. So this is the new system with eta. So now the variable is not x1 but eta 1, and this variable will be eta 2. So all the coordinates is changing here. Yeah, so that's the difference. So what you want to solve for here is basically you're solving for a new variable eta, which is the transform coordinates. Yeah, notice also maybe other parameters will be slightly different than the original form. Maybe in the original system is f1 and f2 small f. The new one will have slightly different or transform values of f1 and f2. Same goes with the mass matrix and the stiffness matrix. Okay, so once you have the solution, okay, so you would need to actually transform back, because what you want basically, previously from here you are transforming from x to eta using this equation. So after solution, okay, you get the solution. How do you get solution? Using a solution of single degree of freedom system. Then you would need to transform back from eta to x, because the final answer should all be in x. Yeah, so that's why you have to transform back. Maybe after an example will be a bit clearer. So here we have an example 1. So let's say we have this system. So in this problem, we give you all the values of m1, m2 and all the c's. We assume all the c's are zeros. Okay, you only have m1, m2, k1, k2 and k3. So if you actually substitute all these values, you can get it in the in this form as the equation of motions, and then you transform it into a form of matrix. After you assume the solutions, you just it's the similar process when you want to find the natural frequencies, because what you want to find is you want to find a matrix of phi, which is the principal the mode shapes vectors. Yeah, so that's why here after that you express the expression as such. Then you take the determinant. Okay, so once you take the determinant, you get the characteristic equation. So the steps are very similar to lecture 10 on finding the mode shapes. Then you get the roots of the characteristic equations, and you see that the two natural frequencies are square root of 2 over 5 and 1 here. Then you substitute omega 1 and omega 2. If you do that, you can get the mode shape. So you want to find the mode shape. So in this case, the mode shape at omega 1, okay, is given. Okay, as in this problem. So basically, if you substitute 1 here, so you can actually get the mode shape is 1, 1. Okay, when x1 is 1, x2 is also 1 because x2 is equals to x1. Okay, the second mode shape, okay, the second mode shape is basically you find that your x2 is equals to negative x1 over 2. So if you substitute x1 equals to 1, then your x2 will become negative 1 over 2. Okay, so these are the mode shapes. So how do you actually write vector or matrix phi? Okay, so these are the values that we have found. So and you get the mode shapes. So if you look at here, basically what the mode shape says that if in the first natural frequency, both x1 and x2 are 1, 1, so it moves the same phase, okay, in the same phase, in the same direction and magnitude, because it's 1, 1. Whereas at the second natural frequency is out of phase, okay. You can see here, this one goes here, this one goes there. That means just now it's 1 negative 1 over 2. So when this moves 1, this one goes opposite side and it moves 1 over 2 here. So that's how you would draw the movement, okay, or the mode shapes of both. You can also draw it as a figure as such. So from there, it means that the system can vibrate freely with simple harmonic motion. So the first part is just getting the mode shapes. So you have to use free vibration in that case. Okay, the second part is still the same system. Okay, but we want to get to do the modal analysis. So we have found that the phi just now, okay, or the first mode shape is 1, 1, second mode shape is 1, negative 1 over 2. So now how we write our modal matrix is basically this will be the phi 1 and this one will be the phi 2. This phi represent mode shapes, yeah, mode shape number 1, mode shape number 2. So that is how we arrange this matrix, modal matrix. Okay, so we've done with our modal matrix, so we can actually transform now, okay, using this equation where your x equals to phi times eta. So these are the modal matrix just now. So you put it in that form, and what you need to do, you substitute into the equation of motion, okay, in this case. So basically you just put your matrix inside. So I'll just copy paste again the original matrix here. So this is the original matrix or the EOM. So if you remember, so basically the next step for you want to get this part diagonal, isn't it? you want to get MD and KD basically. So this is your original M, this is your original K matrix. Okay, so now we want to make it diagonal, so you have to times the mode shapes transpose, pre multiply it with mode shape transpose, and post multiply it with the model matrix. Okay, same you do with this one, so you can get MD and KD. Okay, we follow the previous steps. So after that, if you do that, so you would need to maybe do a bit of revision how you get this value. So basically for each of this, basically 1 times 5 plus 1 times 0. So basically row times column for each of this to get one value. Okay, and then you proceed until you get the final answer. So I do an example here. So basically row times column, and then you repeat for that as well. So if you do that, you have 1 times 5 is 5 plus 1 times 0 is 0. So 5 plus 0 is 5. So that's how you get 5 there. And then you have 1 times 0 is 0. 1 times 10 is 10. So 0 plus 10, so that's how you get 10. So do the same thing for the second row. You have 1 times 5 is 5. So that times 0 is 0. So you get 5. So 1 times 0 is 0. Half, negative half times 10 is negative 5. Okay. So after that step, then only you times with the second one. So if you do that, so you get this answer. So repeat that until you get your, you can see that both matrices has 0 like this, means it is proven that it's diagonal. Okay, so if you don't get diagonal, you must have problem or you must have an error somewhere. So you can see that it is diagonal. You only have value like this. Yeah. So once you have the MD and KD, so you can see that this is how we put the equations. Now you have the MD and KD, so you can see this will collapse into a single equation with only one variable of eta 1, and same as the second one. So you can see there's only eta 1 in the first equation, and in the second equation you only have eta 2. So this is very similar to your single degree of freedom system. So you can actually solve this using your single degree of freedom system. So this is how it looks like, the original system and the new system with eta 1. Okay, oops. So now you have in terms of eta 1 and eta 2. Okay, previously you have x1 and x2 connected or coupled. Now you have eta 1 and eta 2 is decoupled as single degree of freedom system. Two single degree of freedom system. So you use the equation that you have in your list of equations to solve for eta. So you are solving for eta here. So basically, how do you write your x back is based on, once you solve for your what is eta 1 and eta 2, basically you use the relationship between x and eta. So if you remember, you have your phi or your modal matrix times eta. So this is what it is basically. You have your x1. So this will become phi. Remember, it has just now 1, 1. So basically, if I want to write, it should be like this. Then you would have your eta just now. You have matrix 1, 1, 1, negative half just now. And then you have your eta 1 and eta 2. So that is how you get this. You can see that x1, sorry, that's not x, yeah, that should be eta. So you can see that 1 times eta 1 is this one, plus 1 times eta 2 is this expression. And then you have the second equation, you just times eta 1 and negative half eta 2. That's how we get the expression. So then you can solve for your x1 and x2. So that's all. So if you have n degree of freedom system, you can easily expand this. So this is what basically most of the softwares, if they want you use for multiple degree of freedoms, billions or thousands or billions of degrees of freedoms, you can easily expand it in the form of matrices. So that's why it's very important. If you know the steps for 2 degrees of freedom, you can easily expand to more degrees of freedom. Okay, that's all for this video. So maybe check out another video for another examples of the steps how we do modal analysis. And finally, you can get your responses for 2 degrees of freedom system. Thank you.